Hello, I'm Guillermo, and I will be your lead TA this week. And in today's exercise, what we're going to be learning is a bit more about neural networks. In particular, we're going to be delving a bit more on trying to see how backpropagation works and some inner workings of the weight space of the neural networks. But before we see a bit of this exercise, the idea is that before what we saw is that how to use PyTorch to implement complex neural networks with many layers, complex loss functions, different activations. So PyTorch is actually a very useful tool for both researchers and engineers that allows to abstract most of the hard work that you need to do to compute these gradients of neural networks. But in today's exercise, we are going to try to do the hard work. And it is important that we do this because if we implement backpropagation at least once in our life, this will help us understand a bit better how these neural networks work. So the exercise of this week will consist of two parts. A first part, which is a bit more practical, in which we are going to compute feed-forward, implement the feed-forward computations of simple single hidden layer neural network and the backpropagation as well. And a second part in which we're going to do a bit of analysis of this network. So, okay, in the first part of the exercise, we're going to be working with a very, very simple model, which consists of a simple neural network with one hidden layer with 5 neurons and an input layer with 4 dimensions. And this neural network will be implementing a forward pass that will output one scalar y hat. And so in the first exercise, what we ask you to do is just simply follow the computations in this network to get this y hat. So the first exercise consists of using NumPy, so no PyTorch this time, implement the feed-forward pass of this neural network. And this is basically just rewriting these equations in NumPy. Now, in the notebook, what you will see is that first you will have to copy the code that you already have for the sigmoid from the logistic regression lecture, in which we had the sigmoid and the gradient of the sigmoid, and then implement the feed-forward pass. And what you have is some simple test that allows you to see if you have implemented it correctly. So what we're doing is we're giving some example weight values and some input vector. And if your function is implemented correctly, then the scalar that you should get for these specific weights and this specific input should be close to this expected value. Now, in the second part of the exercise, what we're going to be doing is just compute the gradient of this network with respect to the weights, which is what we need for training this neural network. And in particular, we're going to do it for this specific choice of loss. So the idea is that you're going to reproduce the same steps that we have in the lectures for computing the backpropagation, which is nothing else but the chain rule on this loss over the weights in the network. So the first part of the exercise will just consist of you developing the expression for the gradients, first for the weights in the hidden layer, and then for the weights in the first layer, so from the input to the hidden layer, and then from the hidden layer to the output. And for doing this, the only thing that you need to do is just apply the chain rule. So you first take your loss, and then here the y hat is basically the output of your network. So what you need to do is like compute the partial derivative of the loss with respect to y hat, then the partial derivative times the partial derivative of y hat with respect to the weights. And for doing this, as you saw in class, the easy way to go is again creating this variable z1 that allows you to simplify a bit the computation. So just be a bit careful with the computations, and you should get it in the end. So okay, once we have these expressions, what we ask you to do is to write again those expressions in NumPy and compute the backpropagation over this network. And as we had before, we're going to give you some weight values as examples for this network. And if everything goes correctly, you should get the right values for the gradient. So if you implement this function correctly, then your test will pass, and you will know that you have implemented things correctly. Okay, that is the practical part of today's exercise. The second part is a bit more theoretical. In particular, what we're going to see is that even though neural networks are actually very hard to analyze, we can sometimes get some intuitions from modeling them with some of the tools that we have seen in class. So in this exercise, the setup consists of talking about an abstract neural network. So we are not given the architecture of this neural network. What we know at least is that we can write all the weights of this neural network into a vector W. And what we're going to be investigating is a bit what are the properties of the neural network in the weight space, so the space of all possible weights. And for doing that, what we're going to do is assume some structure on the loss. So as you know, it's for neural networks, the loss landscape or the optimization is not convex. So it means that it's very, very hard to analyze. But what sometimes researchers do to try to get some understanding of how this works is to approximate the loss as if it was convex at a given point. And in particular, what we will do is like say that we can approximate this loss as if it was quadratic around a certain point. And the certain point that we would pick is actually the optimal point. So this is nothing else than doing a Taylor expansion of the loss around the optimal set of weights. And what you see is that in this second order Taylor expansion, we don't have any gradient term. And this is because we are assuming that we are around the optimal weights. And the gradient at the optimum, we know it will be 0. So this Taylor decomposition only has, at order 2, has only a quadratic term in terms of the Hessian. And the Hessian here is just the second derivative of the loss with respect to the weights. So it's a matrix. And so the exercise asks you what would happen if now we augment this loss with some regularization term that looks similar to the ridge regression term. And the question is, if we just add here this regularization, how will W start changing? And now the nice thing about this assumption is that we have abstracted all the non-convexity of the problem into something that is indeed a convex loss, at least when you're close to W star. And we can use the convex tools that we have learned, and we can derive the exact minimum of this quadratic function. And what you will see is that once you derive that minimum by making the gradient equal to 0, you will see that the solution will have this form. So the solution of the regularized problem will be the same solution as you would have if you didn't have the regularization term times some matrix. And this matrix will depend on the value of mu, but will also depend on the eigendecomposition of the Hessian. So once we have derived this expression, the next part of the exercise just deals about trying to understand a bit the intuition behind this term. And the first part will go into basically analyzing the eigenvalues of this matrix, which we ask you to see that are actually a diagonal matrix with rescaled eigenvalues by this factor of mu. So you need to just derive this expression for each of the elements in this matrix, and you will see that these are the actual solutions. And once we have seen this, this final exercise just tries to understand what this means in a practical case. So in particular, what we will assume is that we have different eigenvalues in the Hessian. And the question is, depending on the size of this eigenvalue, how much will the regularization term affect? And in particular, what we ask you to show is that for the largest eigenvalues, nothing would essentially happen. So we would get more or less the same component of the vector in that eigenspace, but the regularization would really kick in the directions where you have very small eigenvalues. So in this exercise, we just want you to show this more or less formally that this is indeed the case, and basically build an intuition around this concept. So, okay, that's all about this week's exercise. If you have any questions, just feel free to do it in the chat. Thank you very much.